Imagine I have a function f of x. Let me ask you a pretty weird question. What is the average value of this function over the boundaries where x equals a and x equals b? Think about it again. The average value of a continuous function. Okay, we know the average of a dataset is adding up all the values and dividing by how many there are. When we talk about the value of a function at a point, well, that's just the height of the function at that point. So let's add up all the function values over this interval. Imagine the boundaries are 1 and 5. This point's value is 1.1, this one's is 1.2, this one is 1.2435, this one is 2.475634. Wait a second. There are infinitely many values in this interval. So their sum is just infinity? Well, how many values are there? Well, there's infinitely many values. So the average of this function is infinity over infinity, which cancels to 1. Other than this expression being very indeterminate, we are kind of on the right track with the connection of this problem to averages. The key change is instead of looking at normal averages, we look at weighted averages. Well, what's the difference between the two? Let's look at an example. Say I have a dataset containing the points 1, 1, 3, 5, 5, 5, and 8. We know what the average of this dataset is. You just add up all the points and divide by how many there are. So the average of this set is simply 4. An interesting observation to note is that the 1 and the 5 come up multiple times. So another possible way to frame this is looking at how many times each number appears, adding them up, and dividing by their total frequencies. Let me show you what I mean. The 1 appears twice, so we can rewrite it as 2 times 1. The 3 appears once, so we can rewrite it as 1 times 3. The 5 appears 3 times, so it can be rewritten as 3 times 5. And the 8 appears only once, so it's simply 1 times 8. Now let's divide by the total frequency. The frequency of the number 1 is 2, since it shows up twice. The frequency of 3 is 1, since it shows up once. 5 is 3, and 8 is 1. This result gives the same average, but we reframed it so that it's determined by how many times each number appears, or how much they contribute to the total. The amount a certain number contributes is called its weight. This is conceptually the weighted average formula. Generalizing, if a certain number x1 appears w1 times, and x2 appears w2 times, and so on, then the average is simply summing up all the values, which is the number multiplied by its corresponding frequency, divided by how many overall times the numbers appeared, which is just the sum of all the individual frequencies. So in summation notation, the formula just becomes this: the summation from I equals 1 to n of xi times wi divided by that same summation of wi. While it looks scary, just remember that all it's doing is seeing how many times a certain number appeared, multiplying that frequency by the number, summing it with all other values, and dividing by the total number of times all the numbers appeared. Again, the frequencies tell us how much each number contributes to the whole, so it's better to think of these as the weights of each corresponding number, which shows how much each number matters. If the weight is big, that number matters a lot. If it is small, the number doesn't matter as much. But how does this idea of a weighted average connect to the average value of our previous function? Well, let's go back to sampling some points from our graph. It's always a good idea to start out with a finite number of samples and later evolve into infinite samples. Let's split this interval into smaller subintervals, which I'll represent as rectangles. within each subinterval, let's choose a point to sample. For example, in the first subinterval, we can choose this point. In the second, we can choose this one, and so on. Each sample point is representative of its subinterval. But here's the problem. We never said all subintervals should have equal widths. Some subintervals, along with their corresponding sample points, can occupy more space than others. This means some areas of this larger interval will have more priority than others. So we need a way of controlling this sampling and look at how much each subinterval individually contributes to the whole interval. That's where we bring in our weighted average to get the fairest average. Looking at the formula, well, what are the values of the data points? Well, those are literally the points we are sampling. The value of these points are determined by their y value, or f of x. But the bigger question, what should the weights be? Think about what makes these intervals bigger or smaller than others. Well, changing the width of these intervals changes its size and occupation of its sample point. If each subinterval has greater width, its sample point contributes a lot more to the total. Likewise, if each subinterval has smaller width, its sample point contributes less to the total. Let's call the width of these subintervals delta x for a finite change in the x value. Since the width literally changes the contribution of each sample point, the weight will in fact be delta x. Right now, this is only a finite number of sample points and intervals. To get a true average, we need to add over this continuum, which means we need to decrease delta x to fit more and more sample points. If we take the limit as delta x goes to 0, which means that the width of the interval becomes smaller and smaller so that we can fit more and more points, our summation turns into an integral expression. Delta x in this case is no longer a finite value, but it is instead symbolic of an infinitesimally small width, which is expressed by dx instead of delta x. We are sampling points and their contributions over the total interval from x equals a to x equals b. So our bounds change to reflect that. Take a moment to gut check what this new expression is saying. It's telling us to sum every point and its weight, or contribution, over the interval and divide by the sum of the weights, which is exactly what our weighted average formula did. If you know a little bit of calculus, the integral of dx is the same as 1 times dx. The integral of 1 with respect to x is simply x, and plugging in our bounds from x equals a to x equals b results in our answer being b minus a. So the average of our function over this interval is 1 over b minus a times the integral from a to b to f of x dx. Conceptually, this makes sense. The integral expression of f of x gives us the area under the curve of the function, and b minus a is essentially the width of this interval. Area divided by width gives us height, which is exactly what we're looking for. What's the average value or average height of this function? I want to take a moment and sidestep from this and go to the mean value theorem for integrals. Let's let some value c be an input on the interval from a to b, such that f of c, its output, represents the average value of this function, which is exactly what we found before. If I set these two equal to each other and multiply both sides by b minus a, we get f of c times b minus a is equal to the integral of f of x dx from a to b. The integral expression is the area under the curve, and f of c is essentially a height, and b minus a is a width. Multiplying f of c and b minus a gives you the area under the curve. But you could think of f of c times b minus a as the area of a rectangle, one with a base of b minus a and height of f of c. And this provides a nice insight into the geometric meaning of this expression, as we can now reframe the question of what is the average value of this function into what height f of c should this block have such that its area is the same as the area under the curve of the function. This is exactly what the mean value theorem for integrals is saying, and whatever height you find that suffices the question is your mean value for this function. Now, granted, if you want a more rigorous proof to this, I've linked below a video or a few that might be helpful. This video was more on the intuition and surprising connection between weighted averages and integrals. With that out of the way, I will see you guys in the next one.